Hi, so in this video, I wanted to get into polyprotic acids and the acid dissociation equilibria that are associated with those kinds of acids. As a reminder, a polyprotic acid is just an acid that maybe has multiple protons that it can donate. So rather than just a chemical formula of like HA, right, they're going to have multiple protons at the front of it. So expect things like H2 with some anion or H3 with some anion. For instance, as an example, we can consider phosphoric acid, which is known as a triprotic acid, meaning that it has three protons which can dissociate, right? So three acidic hydrogens on it. Now, the chemical formula of phosphoric acid is H3PO4, and I have written out right here the acid dissociation equilibrium for H3PO4. So just like in any other acid dissociation equilibria, they kind of follow the same format where we have our acid as a reactant and then the conjugate base and H plus as the products there. So right, that separation of the proton from the acid is shown in this dissociation step. Now this dissociation does occur just one at a time, so that's why I've only shown here one proton leaving. But if you look at the conjugate base of H2PO4 minus, right, you can see that that still has hydrogens at the front of its chemical formula, so it still has acidic protons, which can then also be donated. So imagine, right, the H2PO4 minus also acting essentially as an acid, right, when that dissociates, it's going to then produce its conjugate base, HPO4 minus, and then again some H plus, right? So that dissociation step is shown right there. And then because we still have yet another proton at the front of that HPO4 minus, that can also dissociate. And so then we have here this third step of the PO4 minus or phosphate ion being produced, as well as H plus. And so right with this triprotic acid, we see three acid dissociations occur. Those have three corresponding equilibria and three corresponding acid dissociation constants, or Kas. We distinguish those Kas with just a little subscript 1, 2, or 3, right? That indicates which proton is leaving. If it's the first proton, as we see at the top, that's Ka1. If it's the third proton that we see at the bottom there, right, that's Ka3. Now, when it comes to working with problems involving polyprotic acids, it can be a little daunting to see like all of these different acid dissociation steps. And you may be thinking to yourself like, oh my gosh, am I going to have to do 3 ice tables for any of these polyprotic acid problems? And the answer is not necessarily, right? Oftentimes, as you guys have seen throughout the chapter, something that we're interested in with acids is like, what the pH is. So really like what the concentration of H plus or hydronium may be in a solution. The nice thing about polyprotic acids is that all the different K constants, they tend to get smaller as we go further. So for instance, like Ka1 is going to be larger than Ka2, Ka2 is larger than Ka3. And so with every sequential step, right, the dissociation just becomes less and less. So when it comes to the H plus concentration in a polyprotic acid solution, that H plus concentration usually just comes from the first deprotonation, and then it changes very little with each additional dissociation. And so a lot of the time, right, when looking at these polyprotic acids, if we're really just concerned with like what the pH is of the solution or what the H plus concentration is of the solution, we usually don't need like multiple ice tables to handle that. Now that said, there are certain scenarios in which we may be interested in a concentration not just of the H plus, but particularly of like some of the conjugate bases or what's left of, a particular acid. And so in those cases, because the conjugate base itself, as like a chemical formula, changes in each one of these steps, we would then need to actually do like maybe a few ice tables. So let's consider an example right here where I ask you to determine the molar concentration of phosphate ions in a 0.100 molar phosphoric acid solution. So right, we're starting with H3PO4. We want to find out what the equilibrium concentration is for the PO4 minus, that is the phosphate. So that's the very last conjugate base out of these three equilibria. I have here the actual Ka constant values. So as you can see, each one gets a little bit smaller, and so we can use these to again determine this concentration of phosphate for the solution. So let's go ahead and do that right here. I start by first looking at that first dissociation step, right? Because I'm starting with a 0.100 molar solution of phosphoric acid, that is the H3PO4, right? I need to kind of treat that as my starting point here and allow that to dissociate into the next step and then the next step after that. But right, starting first with that first dissociation that includes the H3PO4 in it, I have that first Ka given and the acid dissociation equilibria associated with it. Now what I've done right here is I've set up my ice table with my 0.100 molar phosphoric acid to start initially. And as is usually the case with these kinds of weak acid problems, I have equilibrium concentrations of just like X for the conjugate base, X for the H+, and then my initial minus X for the H3PO4. So I can solve for X itself using this Ka constant. Again, we're using this first acid dissociation because this is the first proton leaving the H3PO4. And so to solve for X, I need to use that Ka1 and set that equal to the products over the reactants. I'm not going to walk through all of the math right here, but basically just using the quadratic formula and algebraically, I can solve for X here as about 0.023 molar. So right, that X is going to go back into my ice table as my equilibrium amounts. So that means then that for the H3PO4, we have a concentration of about 0.077 molar. For the H2PO4, it's 0.023. And then for H+, it's that same concentration. Now again, the question at hand here is not what is the molar concentration of any of these species specifically, right? It asks for the phosphate, so just the PO4 3- on its own, which we don't have yet in this ice table, but right, we can carry things on and start looking at the second dissociation, right? Because we have now this H2PO4- in solution, again, that's going to further dissociate, and so we can start taking a look at the second dissociation step. So again, that occurs where we have our H2PO4- dissociating into HPO4 2- and hydronium, right? This has, again, a different K constant called Ka2 of 6.3 times 10 to the -8. The same rules kind of apply here. We're going to, again, just set up an ice table, solve for X, and then kind of move forward from there. The important thing to note about the ice table that we're going to prepare here, though, is that it's taking the concentrations that we had from our previous ice table at the end and using them as the new initial values. So for instance, the H2PO4-, as we saw from the first ice table, had an equilibrium concentration of 0.023. That is going to now be initial here for the second dissociation, and the same goes for the H+ as well, right? That was also produced from that first step, and so now we have some initial concentrations of both H+ and our acid in this step, right, the H2PO4-. Now the conjugate base here of HPO4 2-, that still is initially 0 as far as we know, right, because we did not see that being produced at all from the first dissociation, right? This is the first time that it's popping up, and so we'll say initially that that concentration is 0. Now again, going through the motions here, right, I can use my ice table, use my Ka constant that I have, and solve for X. Now setting things up, it's important to note that because Ka is so small, the concentration of both the H2PO4- and the H+, those are not really going to change at all. So our equilibrium amount is going to still be basically 0.023. The only X then that actually changes here is for that HPO4 2-, and so we find that the molar concentration of that is equal to 6.3 times 10 to the -8. So now kind of updating my ice table, right, I have the following concentrations at equilibrium, shown right here for all three of the substances in this second dissociation reaction. Now still, we do not have the concentration of phosphate yet, but we are getting very close here, right? What we have now in our solution is HPO4 2- as well as these other guys. As discussed previously, that HPO4 2- can dissociate just one more time, losing that final proton and giving us then the fully deprotonated phosphate. So here I have the ice table for this reaction. Again, the concentrations of HPO4 2- and for H+, those were taken from the previous step ice table. So just whatever our equilibrium amounts were there, those now become the initial amounts for this third reaction. Again, I can kind of set things up. I see that for those two concentrations that start off initially not at zero, they're large enough that the change to them can be ignored. It is the phosphate, though, that will change in concentration, so that's how we're going to solve for x using our Ka expression. Now, solving for x right here, we get a value of 1.1 times 10 to the minus 18, which is a super duper small concentration, I'll admit, but that's kind of to be expected. Again, with each of these sequential equilibria, their Kas are going to decrease by a lot. And so by the end of this dissociation, right, the amount of actual product coming from that is going to be really, really, really minimal. And so that's reflected right here in our concentration of phosphate. But still, it's important for us to know what that final concentration is, even though it's very small. Again, though, what may be more important to us, generally speaking, is the concentration of H plus alone. And as you guys saw through the previous steps, right, the H plus concentration, it ends here as 0.023 molar. That was exactly what it was at the end of the first ice table. So I didn't need to necessarily use these additional ice tables to find out the H plus concentration. It's only to find out the concentrations of maybe our other conjugate bases or what's left over of an acid. Where we're concerned with those amounts, that would be then why we would need maybe multiple ice tables. Now, there is one other scenario involving polyprotic acids that's a little bit more specific, and I do want to highlight it for y'all. So as was seen in a previous slide, most polyprotic acids are weak acids. So like the phosphoric acid, for instance, not just like in Ka3, but in Ka1, that first acid dissociation, that was a small Ka value. And so that's true for pretty much all of our different polyprotic acids. The only exception to that, though, is sulfuric acid. Remember that sulfuric acid is on the list of strong acids to remember. And so when we consider solutions of sulfuric acid, right, we do want to be a little bit more careful with it because it has that strong acid dissociation. So to get us started here, I want you to practice writing out acid dissociation equilibria for a polyprotic acid. So for sulfuric acid, it's a diprotic acid, so we expect to see two acid dissociation equilibria for it. Go ahead and write out both of those, both the one for Ka1 and the one for Ka2. You can pause, write that out, and then I'll show you the answers in just a minute. All right, so hopefully you've taken some time to write out the acid dissociation equilibria for sulfuric acid. As a reminder, sulfuric acid is H2SO4, and so when it dissociates, right, that first dissociation is just going to be losing the first proton. So starting with H2SO4, we turn that into HSO4 minus as well as H plus. This has an acid dissociation constant of Ka1, we'll call it. And again, because this is a strong acid, Ka1 is going to be very large, right? I show it here as much greater than 1. Now, because that Ka is so large, I think of it less as really an equilibrium and instead just like a complete forward reaction. So this dissociation, right, like any strong acid dissociation, really does basically just go to completion. So any amount of H2SO4 that I have, that's going to completely dissociate into HSO4 minus and H plus. The HSO4 minus then, because it still has an acidic proton on it, can undergo the second acid dissociation shown right here. In that case, our products are again H plus, but now also sulfate or SO4 2 minus. Now the second acid dissociation is a little bit weaker, right? It has a Ka constant of 1.0 times 10 to the minus 2. And so, right, while that first step goes to completion, that second step is still technically a weak acid. It's still rather strong as far as weak acids go, right? 10 to the minus 2 is not that small of a Ka value, but how we think about sulfuric acid problems, right, does require this distinction because it's not a weak acid to begin with. So let's look at an example where I want to find the pH of a 0.500 molar solution of H2SO4. For this, I'm going to, again, kind of start from the top and start with that first acid dissociation and look at that all on its own. Now for that first dissociation, because it is so strong, how that looks is more like just a limiting reactant type problem. So I might set up not necessarily an ice table, but instead what I call a reaction table. It's really just the same thing. It's like an accounting method to keep track of our concentrations of products and reactants before, during, and then after a reaction. So the distinction here is just that there's no K constant really when solving for these. What we go by is just based off of what our limiting reactant is, right? When the limiting reactant runs out, that tells us how much of the product we can make from it. But so I set it up here just kind of very similar to how I would set up an ice table. I start with my initial amounts at the top as the before line. In this case, that's 0.500 molar of the sulfuric acid. The after line is in part decided by whatever my limiting reactant is. So because I have only one reactant here, the H2SO4, I can assume that that's going to completely run out. And so after the reaction is over, right, it ends with 0. And so what that tells me then is that the H2SO4 itself changed by negative 0.500, so that the before plus whatever the change is, that equals the after. So it is, in essence, operating the same way that the ice table does, right? These first two lines add up to that third line. It's just how we decide what the change itself is, that like X variable. X here is just dictated by whatever our limiting reactant is, ensuring that that limiting reactant runs out. Now what that also means then is that for our products, because they have the same molar coefficient as the H2SO4, each one of those are going to increase by the same amount. So 0.500 is added to both the HSO4 minus and the H plus. And so then after this first reaction, again, going to completion here, we now have the concentrations of both HSO4 minus and H plus, at least after this first dissociation step. However, that HSO4 minus is followed up with a second dissociation shown right here. Again, this will result in then the fully deprotonated sulfate ion as well as more hydronium. And the Ka constant for this second step is Ka2, right? That's given with this equilibrium. Now for this, because this is an equilibrium, we're going to do like just a true ice table here. So I have my initial concentration of HSO4 minus taken from the reaction table from the previous step. Also, the initial concentration of H plus was taken from that same reaction table. So both of those will say initially start at 0.500 molar. For the sulfate, however, because that is like brand new here, right, that's going to initially start at 0. And so we can see how our products and reactants change in terms of X, setting up our ice table like so. Now in this scenario, the Ka itself is still relatively large, and so we can't really ignore the change to either H plus or HSO4 minus. And so we're going to have to go through and like really solve for X in this case, plugging into our Ka expression and then solving algebraically. I encourage you to like pause and work through the same example on your own just to make sure that you're doing the math correctly and everything. And then when you're ready, we can unpause and we'll talk through just how we solve for X here. All right, so plugging things into the Ka itself, again, that is like the concentration of SO4 2 minus times the concentration of H plus divided by the concentration of HSO4 minus. I've taken those equilibrium concentrations from my ice table and placed them in right here. Going through all of the math for this, right, I'm going to multiply both sides by the denominator of 0.500 minus x. That gives me then this expression. Then I can kind of combine some like terms. I want this to look like the proper format to plug into the quadratic formula. And so I'm going to need to put all of my x's together, all of the x squareds together. And it gives me then this equation of 0 equals x squared plus 0.490x minus 0.0050. Now this is ready to then go into the quadratic formula. I have my b as 0.490, I have c as negative 0.005, and then I have a as just 1. Going ahead and solving for that, I find that x is equal to 0.01. So what that tells me is that my concentration of H plus is not 0.01, but again, refer back to the ice table itself. The concentration of H plus started here as 0.500, so we can add on to that 0.01, giving me then a concentration of 0.51 for the H+. So what that means then is that the pH of the solution is 0.29. So again, when we're looking at solutions of sulfuric acid, it does kind of inherently require two ice tables, right? The first one I treat a little bit differently because it's like a limiting reactant for the first association, but then the second one is like a true equilibrium, and so we can go about solving it just using our regular ice table method, solving for X, and then finding the pH that way, right? But so that kind of introduces us to the idea of polyprotic acids. We'll see these come up again in the next chapter a little bit as well, but please let me know if you have any questions, and I'm always happy to help. Bye.